Right, this is really awkward. I was teaching Akira, Casey.
Thanks.
You guys are in video now.
And others, and it just became apparent, rather than me wasting all my time going through this again and again and again, it might be useful if I just stick it on YouTube and then you can have a look at it. It gives your heart's content. I'm just going to go over basic uncertainties and basic absolute uncertainties so that you can go and have a look at that in your own time. One thing to become aware of, this book here, I've ordered about 50 copies. Thank you. Doing an excellent job there, Levi. I've ordered 50 copies. They have basically a ton of problems from AS and A2 parts of the course. So it'll be useful for year 12s and year 13s. It's going to cost £1 to buy one. If you buy one, then it'll be useful for both this year and next year. And it just means you can do tons and tons and tons and tons of practice before you sit your exams in late May or early June. Okay. So, first things first, I'm going to talk largely to you guys just because I don't want to stare at Levi's face for any longer than absolutely necessary. Right, so precision and accuracy are two terms that you're going to need to become very aware of. I'll go through all the terms first and then we'll look at other nomenclature that you're going to need. So, first one, precision. It's how many significant figures your equipment can measure to. Something can be incredibly precise and have lots of increments on it, like a meter ruler, but only be 30 centimeters long and therefore horrendously inaccurate. Accuracy is how close your result is, how close the reading you've got is to the right answer. So if you've got a clock that is an hour fast, because it measures the nearest second, it will be very precise, but because the answer is inherently wrong, it will be inaccurate. Now, precision is only impacted by the number of increments on the piece of equipment. Accuracy can be measured by one of two types of uncertainty. These uncertainties are random error and systematic error. Random error is something which occurs at random. It's impossible to account for, and you don't know to what extreme it's going to occur. So a good example of random error is human reaction time. It's difficult to account for. Systematic error is something which is an issue with the system. Okay, so something like a clock being 2 seconds fast or slow. Systematic error is predictable and can sometimes be resolved by calibrating the equipment. It's important to note at this point that something could be a systematic error and be impacted differing amounts at different levels. So, for example, if we're looking at resistivity or resistance, as you increase the current running through a wire, then you're going to get a heating effect, and that's going to produce a systematic error with your resistance reading. Now, obviously, the more current you pass through, the bigger this systematic error is going to become, but at least you can predict it. It's not going to go up and then down and up and down. It will increase by a bigger amount as you go further along, but it is at least predictable. Okay? Right, so those are your key terms: precision, accuracy, random error, systematic error. There is one subset of systematic error, which I'm going to put up here, and that is zero error. Okay, or a zeroing error. And that is when a piece of equipment is at its 0 point, not 0. So for example, if you stand on a mass balance or some weighing scales, and before you stand on it, when it should be at 0, it's at 2 stone or 20 kilos or whatever, then it hasn't been zeroed properly, and that's a key example of a systematic error. The way you deal with that, quite surprisingly, is to calibrate it. If you can't calibrate it, because there isn't the facility to do so, you deduct the extra reading at the 0 point. Okay, so that is to say, if it reads 3 kilos with nothing on it, whatever your reading was, you take 3 kilos off it. So if you've got 27 kilos with something that started off at 3, when there was nothing on there, your actual reading is going to be what, Casey?
If you've got 7, sorry.
So you've got a reading of 27,
yeah,
and with nothing on it,
yeah,
what it was 3 kilos. So what's its actual weight?
24.
24, exactly. Okay, and so that's another way that you can account for zero error. Okay, let me just grab some. Levi, if you want to hold steady on that, just so that people can see it. I'm ignoring how uncomfortable this is for everyone involved, and we'll move on to the next bit. Okay, everyone happy? All right. Beautiful. All right, cool. Let's move on.
Are we doing this all in one take, or should I
Let's do it all in one take. Otherwise, there is absolutely no way I'm wasting my time editing this. It's crap enough that I have to do it. Right, so.
It's amazing. We're talking about crap.
We're going to deal first with absolute uncertainty.
I am filming.
Okay. Now, the first bit of absolute uncertainty is precision. Okay, now precision is how many significant figures you can measure to. Okay, a meter ruler, if you were to record all of its increments, if we were to measure 50 centimetres, it would be 50.00 centimetres. It is that because on a meter ruler, you measure to the nearest millimetre. That means on a complete meter ruler, you've got your 100 meter readings, centimetre readings rather, and then you've got another 100, you've got another 100 millimetre readings, 10 for each one of the centimetre. So therefore, that means you have got 10,000 increments, right? 10,000 increments on your centimetre, on your meter ruler. And so therefore, when we measure on a meter ruler, we need to measure to the nearest millimetre. That we can measure to the nearest millimetre. So our precision is the nearest millimetre. We would write it as 50 centimetres plus or minus 1 millimetre. I've just realised that that's been horrendously badly done. In fact, ignore everything I just said. Because I did 1 in centimetres, another 1 in metres. This is a classic example of how even... Thank you for the support, folks. That's an amazing example of even how supremely intelligent people like myself can make horrendous mistakes. Horrendous mistakes. And if I can be asked, I will edit that out.
No, keep it in.
So 50 centimetres, right, so it's going to be 50.0 centimetres, which means that our precision is 0.1 centimetres. Because we can divide each centimetre into 10 millimetres. Okay? So you're going to go, with your precision, you will go to the smallest increment. If we were measuring 27.3 volts, our precision would be plus or minus 0.1 volts.
Okay. Does the voltmeter measure to 0.01, or is that the ammeter? This is what is different.
It depends on the equipment. So if it was 2.73 volts, then it'd be plus or minus 0.01. All right. So your reading determines your precision.
Okay.
Okay. So your precision is the smallest increment you can measure to. Right. If we have a range, it's slightly different. So let's say I've got three readings. I've got 26.5, 26.3, and 26.1. Keep it nice and easy. To work out that uncertainty, the precision is going to be what, Levi?
Plus minus 0.1.
Right, good. So the precision would be plus or minus 0.1. But if we look, whatever our average is, if we plus or minus 0.1 off our average actually means 26.3, which are the numbers I've used, then that means that our uncertainty would only take us up to 26.4 and down to 26.2, which doesn't represent the full range of our data. So we're going to let our range determine it. What that basically says is the precision of our equipment isn't our largest uncertainty, which is quite nice to know. So what we're going to do is we're going to take our range. Now our range between these two values is 26.5 minus 26.1, our largest value minus our smallest value, which gives us 0.4. So our uncertainty, if we take our range, is going to be half of that. So plus or minus 0.2. So whenever you've got more than one reading, we use half the range. Take the full range between the biggest and the smallest, halve it, that's your uncertainty. Okay. Now we call these absolute uncertainties because they are in the units of our reading. This is plus or minus 0.1 centimeters. This is plus or minus 0.1 volts. This is plus or minus 0.01 volts. So an absolute uncertainty means an uncertainty with units. Okay. If in doubt, whether to use the precision or whether to use the range uncertainty, there is one rule. Pick the big one.